Today I am going to discuss about the design procedure of the lateral supported beam. So, beam will be designed on the basis of laterally supported or laterally unsupported. So, today we will discuss only about the laterally supported beam, where its wave will be supported laterally, so that the lateral torsional buckling may be prevented. So, in this case we are assuming that lateral torsional buckling is prevented, and with this what will be the design criteria, that will be discussed, and that is given in the code in clause 8.2.1. In clause 8.2.1 of IS 800/2007, the detail has been discussed, where the design bending strength can be calculated in two cases. One is for low shear, another is for high shear. Low shear means when the shear force is less than the 0.6 times the design shear strength, then it is called low shear. That means, if Vd is the design shear strength of the cross section, then if V is less than 0.6 Vd, then we can call as low shear. That means, shear force is less. So, in case of low shear, we can find out the design bending strength simply by from this formula, that is Md is equal to beta B into Zp Fy by gamma m0, right. Md is equal to beta B into Zp into Fy by gamma m0, where Md is the design bending strength and beta B we can consider as 1 for plastic and compact section. For plastic and compact section, this value beta B can be considered as 1, and for semi compact section we can consider Zd by Zp as the beta B value, right, where Zd is the elastic section modulus and Zp is the plastic section modulus. So, the ratio of Zd by Zp can be found as beta B, and for semi compact section this beta B value will be calculated and will be used, and for plastic or compact section beta B value will be considered simply 1, and whether the section is plastic or compact or semi compact, that will be decided from the codal provision, because from the thickness of the wave and width of the, depth of the wave and other criteria like flange thickness, flange width, etc., we can find out whether a section is compact, plastic or semi compact from the code, and from that basis we can find out the beta B value, right. And Fy is the yield stress of the material and gamma m0 is the partial safety factor. So, Fy can be found for different material, it will be the yield stress value will be different, which also we can found from the code, and gamma m0 is the partial safety factor, which is found in table 5, right. And to avoid irreversible deformation under serviceability loads, we have to maintain these conditions. Like for simply supported beam, Md should be less than 1.2 into Zd Fy by gamma m0. So, Md value whatever we have calculated earlier, in any case it should be less than this value. That means, the Md value calculated earlier, if it is more than this, then we will take this value Md. So, Md is 1.2 into Zd Fy by gamma m0 for simply supported beam, and for cantilever beam we can consider Md as 1.5 Zd Fy by gamma m0. So, Md value should be less than this or this, depending on the support conditions. So, once we find the value of Md, then we can go ahead for next. However, if we see that the shear force is more than the 0.6 times the design shear strength of the beam section, then we can use this formula. that is MD will be equal to MdV, where MdV can be calculated from this. So, when the section is under high shear, that means when the beam is under high shear, that means when V is greater than 0.6 Vd, then the design bending strength can be calculated as Md is equal to Mdv, where Mdv is the design bending strength under high shear, and it can be calculated as Mdv as like this, and it can be calculated for plastic or compact section from this formula. If the section is plastic or compact, then we can find the Mdv value as Md minus beta into Md minus Mfd, right. And in any case it should be less than or equal to 1.2 Jd Fy by gamma m0. So, you have to consider this criteria, it has to be less than this, and Mdv can be calculated from this, where beta is this, beta is 2 into V by Vd minus 1 whole square. So, beta is a coefficient which can be calculated from this formula, and then we can find out the value of Mdv, right. And here Vd, the design shear strength, can be calculated as governed by the wave yielding or wave buckling, and Vd is simply Av by Av into Fv, where Av is the shear area and Fv is the design shear strength. So, Av the design shear area can be calculated as d into Tw for rolled section, where d is the overall depth, Tw is the thickness of wave, and small d into Tw for welded or built up section, where Tw is the thickness and d is the effective depth, right. Here remember, the for rolled section this capital D is the overall depth, right. So, Av can be calculated as d into Tw for rolled section and small d into Tw for welded or built up sections, and Fv is the design shear strength and V is the factor shear force, which we can calculate from the loading condition and from boundary conditions, right. So, once we calculate V and Vd, then we can find out the value of beta, and then we can find out the value of Mdv, right. So, Md is the plastic design moment of the whole section, disregarding high shear effect and considering wave buckling effect. So, Md already we have calculated as a plastic design moment of the whole section, where we are not going to consider the shear force effect, and Mfd is the plastic design strength, which can be calculated from this formula Mfd. Mfd is the plastic design strength of the area of the cross section excluding the shear area, right. So, in case of a section, we have to find out the Mfd value, which is called plastic design strength of the area of the cross section excluding shear area. So, Mfd value we can find out as d square Tw by 4 into Fy for built up section, right, and Mfd is equal to capital D square Tw by 4 Fy for rolled section, where d is the overall depth and small d is the effective depth, that is capital D minus 2 Tf. That means, if we have a section like this, then we can find out this is as capital D and this is as small d, which is capital D minus 2 Tf, right. So, Mfd can be found from this formula depending on the type of sections, and then we can find out the Md value and then Mdv. And for semi compact section, simply we can find out the value as Jd into Fy by gamma m0. So, for semi compact section with high shear, the Mdv value can be calculated from this formula, which is called Jd Fy by gamma m0, right. So, after designing the shear bending, then we will go for shear, right. So, regarding shear, clause 8.4 describes the criteria. In clause 8.4 it says that the factor design shear force should be less than the nominal shear force by gamma m0, V n by gamma m0, right. So, V, the factor design shear force, should be less than or equal to V n by gamma m0, where V n is the nominal shear strength of a section, and V n value can be found from this formula, A V F y w by root 3. A V is equal to shear area, and we have shown how to calculate the shear area, and F y w is the yield strength of the wave, right. So, V n, the nominal shear strength of a section, can be calculated from this formula, where V n is equal to A V into F y w by root 3, where F y w is the yield strength of the wave and A V is the shear area, and the factor design shear force V should be less than or equal to V n by gamma m0. Now, shear areas can be calculated as given in clause 8.4.1.1, where it is told that the shear area A V can be calculated for different type of sections, like for hot rolled section, if major axis bending is happening, then this is d into T w, d is the overall depth, and for major axis bending for welded section, it will be small d into T w for welded section, and similarly for hot rolled or welded section about minor axis, it will be 2 into B into T f, because the flange is in two side. So, 2 into B into T f, right. So, for hot rolled or welded section about minor axis bending, the shear area will be 2 into B into T f. Similarly, rectangular hollow section loaded parallel to height will be this, A into D by B plus D. D is the total depth and A is the shear area. And rectangular hollow sections loaded parallel to width will be A small b by B plus D. So, one is A capital D by B plus D, another is A small b by B plus D, and for circular hollow section it will be 2 A by phi, and for plates and solid bar it will be A is the cross sectional area. So, this is how the shear area of a section can be calculated, which has been given in clause 8.4.1.1, from which we can calculate the shear area A V. Then coming to wave buckling. So, now for wave buckling we can see that the wave behaves like a column if placed under concentrated load. That means, if we have a I section, say for example here, then if we have a concentrated load, say this is a beam, and if we cut this section, so this is section A, right. So, if we see now, because of the concentrated load on the wave at a particular point, so this may buckle depending on the type of member, it will buckle. So, if the wave is thin, then it will come to buckling, or sometimes it may cripple also. It may cripple because of the concentrated load. So, we have to avoid this buckling and crippling. We will come into come in details how to restrict this wave buckling and wave crippling. So, as the wave behaves like a column, therefore, the wave strength we have to calculate the strength, means the vertical compressive strength near the center of the wave, we have to calculate, and then we have to check whether it is safe or not. So, for calculating wave buckling, for different cases the effective depth has been given. Say for example, when the wave is restrained against lateral deflection and rotation, the effective depth is considered as d1 by 2, right, where d1 is the depth of the wave. And if it is restrained against lateral deflection, but not against rotation, then the effective depth will be 2/3 d1. And if restrained against rotation, but not against lateral deflection, then effective depth will be d1, and not restrained against rotation and lateral deflection, the effective depth will be 2 d1. So, the effective depth of the wave can be calculated on the basis of the restraint condition, and that is given here, that if restrained against lateral deflection and rotation, it is d1 by 2. If restrained against lateral deflection, but not against rotation, then 2/3 d1. If restrained against rotation, but not against lateral deflection, then d1, and if restrained against both rotation and if not restrained against rotation and lateral deflection, then effective depth is 2 d1. So, this is required to calculate the compressive stress of the wave. Now, wave buckling strength we would like to calculate. So, for calculation of wave buckling strength, we need to find out how the bearing plate is going to be provided to minimize the wave buckling, means to reduce the wave buckling. Say for example, if a member is subjected to concentrated load at certain point, say concentrated load P is there, and this is called bearing plate. Right, bearing plate. Now, and if we have a support here, then also there is a chance of wave buckling here because of the reaction at the support. So, here also we need to provide bearing plate, and below concentrated load, if we provide the bearing plate, then the load will be dispersed with 45 degree angle. This is the flange, and if this is neutral axis depth, then this will be the width for which we have to calculate. This is B, right, and this B value will be B plus 2 into N1. N1 means if the angle of dispersion is 45 degree, then this value is called N1. So, N1 is the length from dispersion at a 45 degree angle to the level of neutral axis. So, we can find out B as a B plus 2 N1, where small b is the bearing length. This is small b, right. So, this is N1. So, B plus 2 N1, right. So, and in this case, if it is like this, so if I consider this is as B1, then at the support B1 will be simply B plus N1, right. So, the buckling strength below the concentrated load FWB, I can calculate it as B into TW into FCD. Buckling strength can be calculated as this, below concentrated load. Right, and at support buckling strength will be B1 into TW into FCD, right. So, where FCD is the allowable compressive stress corresponding to the assumed wave start according to buckling curve C, right. So, FCD value is the allowable compressive stress and it can be calculated corresponding to it the buckling class C. So, if we know TW is the thickness of wave, TW is the thickness of wave. So, if we know the value of FCD, value of TW and value of B or B1, then we can find out the buckling strength of the member, right. Now, here the when we are going to calculate the design compressive stress FCD, we need to know what is the value of lambda, right. So, lambda means the slenderness ratio. So, slenderness ratio we know, we can find out LE by R. R means in this case RY, right. So, LE, the effective length of the strut LE will be 0.7 d. So, if we consider this 0.7 d by RY, RY means IY by A. So, I can find out 0.7 d by this is IY by A, IY means BT cube by 12 into A is B into T. So, this will be 0.7 d by T by root 12, right. So, lambda we can find out as this. So, after calculation lambda will be 0.7 d into root over 12 by T, this will be around 2.5 d by T. So, for an idealized wave strut, the slenderness ratio lambda can be found as 2.5 into d by T, from which the slenderness ratio can be found, and for buckling class C we can, and for a particular grade of steel we can find out the value of Fy, we can find out the FCD value from these parameters. So, FCD value we can find out the compressive stress, allowable compressive stress. Once we can find out the FCD value, I can find out FWB, that is the buckling strength, wave buckling strength can be found. Now, we will discuss about the wave crippling. For which it may fail. Wave crippling means when a member is under concentrated load. Say for example, we have a support condition here, we have a support condition here. So, it may fail at the root like this. So, wave crippling may occur due to concentrated force at the support, due to concentrated force, right. Otherwise, in other case also it may fail, like say if a concentrated force is applied at the beam at a certain point, then also wave crippling may happen. So, now we have to find out the wave crippling strength, so that we can design accordingly, right. So, here it is the concentrated force is P, right. Now, to know this, we have to find out the FWC. FWC is basically B1 into TW into FYW by gamma m0, right. So, B1 into TW is the area and FYW is the yield strength of the wave, right. So, B1 into TW we have to find out, this is the area. So, this B1 is what? B1 is the bearing length. So, B1 we can find out considering an empirical dispersion that through the planes to the wave planes connection at a slope of 1:2.5. That means, if we have a load here with a bearing length of B, so this is bearing length B, and we assume that a dispersion of 1:2.5 slope it is dispersing. So, at the if we consider this, if this is the flange and if this is the root radius, then this value will be basically Tf plus R1 root radius, Tf plus R1, and this B1 will become B plus 2N1, right, 2N1, and N1 is basically 2.5 into Tf plus R1, right. So, what we can see that we have to find out the dispersion length, which is B plus 2N1 for concentrated load, and if it is under support condition, then it will be B plus N1, right. Now, N1 is 2.5 into Tf plus R1, because this is Tf and this is R1. So, Tf plus R1 will be the depth. So, dispersion will be Tf plus R1 into 2.5. So, once we find the dispersion length, then we can find out the total length B1, and B1 if we find out, we can find out the FWC, the crippling wave crippling strength. So, if this wave crippling strength is more than the load coming into the member at that point, then it is fine. Otherwise, we have to increase the section or increase the wave width, so that wave crippling can be avoided, right. So, in today's discussion, what we have seen that primarily the beam has to design due to moment, and then we have to design due to shear, and then other criteria. So, moment carrying capacity, the design bending strength of the member can be found for two criteria. One is for low shear, another is for high shear. So, in the codal provision it is given for low shear how to calculate the design bending strength, and for high shear how to calculate the design bending strength. Then once design bending strength is calculated, we will go for calculation of the shear strength, and the design shear strength, if it is more than the design if it is more than the shear force acting on the member, then it is fine. Otherwise, again we have to redesign by increasing the section size, right. And also we have to check whether it is means it is safe under wave crippling and wave buckling. So, those criteria has to be also fulfilled. Of course, we have not discussed about the deflection criteria, which also need to be fulfilled. That means, we will find out what is that maximum deflection coming on the member due to the load and support condition, and what is the limiting deflection, and if the criteria is satisfying, then fine, otherwise again we have to redo. So, this is how we can design a beam which is supported laterally. So, laterally supported beam, how to design has been discussed. In next class we will go through one example of the laterally supported beam and we will see how to design that beam. Okay. Thank you.